already a question. First question. Okay. Okay. Thanks. So I'm going to pretend to be English speaking. And I was trying to find the excuse why, and good excuse I couldn't find. So I think the best excuse is it's better for you, because if I start translate the terms in Russian, it will be a disaster. Okay, so human actions. So here is the plan for today. So there will be 2 hours today and 2 hours tomorrow. So this is the plan for today. So I will start with some motivation, going to history, so I will have 2 parts. So one is on human pose estimation. So this will be on still static images. So pose estimation, because it's related to action recognition. And so I will also go through appearance-based and motion-based methods, which are been developed a bit earlier, but I think they're still good to know. And tomorrow, so there will be another set of topics which will be more on spatio-temporal and more modern descriptors. And the practical which you will have tomorrow will be also on spatio-temporal bag of feature actually approach, the similar one which you had for image classification today. So there will be a related practical for video classification tomorrow. Okay, so actions. So when you think of action, so you think of maybe action movies. So here it is. So what's the point? So you see the actor. So you don't know anything what was before. You don't hear the sound. So yet you can easily interpret. So the guy is now running, and he seems to be worried. And so he's worried. So he sees something. Okay, so here somebody get kidnapped. Now, so what do you want to do? So computer vision, so this is not probably the end goal, but this is one of the great things we would like to achieve, is actually very, very simple for us humans. So just to look at this short piece of video and say, for example, that this is indoor scene, the person is drinking, or so there is a building and the people here, and so kidnapping scene and so on. Okay, so this task is quite challenging for computers, as you probably know, but nevertheless, so people have been doing lots of progress in different areas. So this is object recognition, action recognition, scene understanding, and so scene geometry, also maybe understanding the mood of people, are they happy, are they sad, and so on. So all this is currently progressing. So there's lots of in vision conferences, lots of these topics are addressed. And interestingly, so there are all of them, they are related. So for example, if you think of scenes and actions, and I will illustrate this a bit tomorrow. So if you, for example, eating is in a restaurant and so on. So all these things are interconnected. So even if these pieces, they seem very difficult to do. So if you now think of a system which eventually could do everything, you could think that it eventually will use all these constraints between different parts and make the consistent interpretation easier. Okay, and so I will mostly talk about this part. So you had heard about object recognition and maybe a bit of scene geometry previously. So I will be mostly talking about actions, but they will be related to other pieces. So I will start with a bit of a history. So motivating why human actions, when did people start looking at this? Probably this is very long time ago. So here is one example which is documented. So here is Leonardo da Vinci. So he was teaching his students how to draw the nice looking pictures. So, and he was saying that the picture will not look nice if you don't respect, for example, the gravity points, and things like this. So he was taking care about the human body and so on. So that was interesting for producing nice pictures. Okay, so a few 100 years later, so there's another guy, also Italian, so he was interested in how much people can work and how much people spend energy and why and so on. So he was more practical. So a bit further to our time, so with the beginning of photography, so people started to make static photography, and also this was the beginning of cinematography era, so that was all exciting. People started to look at how moving pictures are there. So this is getting closer to computer vision era. So here is a Swedish psychologist. So he was very interested in understanding human motion, and he was presenting the dot patterns to people and asking, so what do they perceive? So if you haven't seen such image before, so you can try to guess what this is. And maybe this is hard, but once the dots start moving, even if the temporal sampling is very coarse here, so 1 frame per second, so you perceive very clearly what's going on. So that was motivating lots of early computer vision work on human perception, and I will be talking more about this. Okay, so here is a timeline. Okay, now so modern computer vision. So what are the? Why are we interested in actions? So okay, so this is the movie most probably all of you have seen. So we see here some marker systems, but apparently so only markers don't work. So they need to have some real computer vision to capture all the small details of the faces and so on. And interestingly, so if you compare these two things, so it's basically the goal has not changed. So the Leonardo da Vinci was teaching his students how to draw nice-looking pictures, and now we are teaching computers how to make realistic videos. So, but the goal is the same. So there is lots of work in graphics which are exciting about video and human action. So here is one example from already a few years back, which here, so this is a in-painting example. So if you don't know this paper, so you may think there is something sophisticated going on. Actually, here is very simple. So what is done here? So somebody just to define the rectangle to remove this piece, and what's going on? So it's the method does copy-paste of patches from other places in the video into. So okay, so maybe you've seen work on in-painting for images. So this is a quite interesting work on in-painting in video. So there is lots of graphics things going on which are exciting. So here's another one. So here's Greg Mori in Berkeley. So he's a PhD student by that time, and he likes football, but he doesn't get to the World Cup. So instead he writes the program, and here he is. So by the way, this is work from Alyosha Epros and others from Berkeley. So, and not just one copy, but many of them. So again, so techniques are, I will talk about how this is done in a moment. Okay, so graphics is great, but there are other applications. For example, if you want, we can think of helping different people. For example, professionals who are doing news analysis. Maybe they make a news program. They have to analyze lots of videos. Maybe you have a big video collection at home. So we came across the papers in sociology. So they were asking students to watch about 900 hours of movies and mark how often do people smoke there. And then they were correlating these numbers with adolescent smoking. So basically how the smoking of main actors influences the people smoking in the society. So this is, so I don't know, it's not clear. Anyway, so we think that this is obvious example, but maybe there are many more examples which could be interesting for them. Okay, so now there is a big area surveillance. So people are debating whether this is surveillance. It has lots of privacy issues, at least in Europe and US. Nevertheless, so here is one video. So if you haven't seen this, you may think that nothing is going on here, but nothing special going on. But if this is your cat, so you care about this video. Right. So the people who discovered this, obviously the owners of this cat, they were very happy that they had a surveillance camera installed. Right, so this woman here, because of this video, she was finally, the police got her. It was in UK about 1 year ago. Okay, so so I hope it's convincing. There are applications out there which would be interesting to solve. So in more scientific sense, so what is action recognition? Is it like a separate domain? Does it have anything to do with, for example, what you heard during this week? So I think it has lots of things in common. Okay, so let's look at an image. So there is no humans here. So what typical, what Andrew was telling you, so classification, object recognition. So there is, with the current methods of computer vision, so we can do many things. So the cars are easy objects. So we have lots of training data for it. So lots of classifiers say, okay, so our algorithm can do a pretty good job. So is this the end? So are we done with computer vision? Okay, so of course we think it's not. So what's next step? So there are, for example, ImageNet. So people are thinking now, okay, we can do pretty well on a few classes. So okay, let's go for lots of classes, lots of images. Of course, this is very good. But is this the end? Okay, so this is an example of one class. So if you don't know, ImageNet is built actually on WordNet, and WordNet is a big tree for English, connecting all English words in a tree or in a graph. Okay, so there is the effort of building the large data set with images for all visual nouns and now even other verbs and maybe adjective for this, and so they have lots of different classes. So here's one class, and I realized that I didn't know the name of this class on any of the languages. So the question is is this the failure? So if it means that I cannot recognize this class or not. So obviously not, because when you come to airports, so even if you don't know what this thing called, even if you've never seen this before, so what is helping you is to look what people do with it. Okay, so human action seems to be a very important cue for us people to understand things, even if we don't know particular objects. Okay, and going back to this picture, so so if we are given a particular task, so how far can computer vision bring us? So for example, say our task is to get a taxi, and we see the taxi is over there. So it's probably not wise to run there, okay? So because you want to know that the car will run over you. So it seems quite important not just to know the name of the object, but also to know what they're useful for, and predict how the world will react and interact with us. Okay, so here's another example. Lots of funny images, not very funny, but okay. So this is what the maybe a good detector trained on Pascal data would give you, and maybe by looking at this image, maybe you want more. Maybe you want to know computer to say that there's something, not just the airplane, but there is something more complicated here. Okay, with this, okay, back to this example, so we can maybe get the labels, get the bounding boxes, get even the segmentation. Still, it will not give us any clue that this is something special here, and that this is something different from millions of other frames from the same camera which computers see. So there is obviously something is missing, and so the field is quite unexplored. So I'm trying to convince that human actions are quite important, not only for particular applications, but also as a part of computer vision. Okay, so here's another one, the last example. So, okay, so what is the difference between these two pictures? Well, they are all the same. So they have same objects, same action. They are pouring water on something, but completely different. So what is the difference? The context is different, yes. The goal, yes, the aim. The aim is different. And the goal and the aim, so this is something completely unaddressed in computer vision currently. So people talk about actions, but not actually what this the actions can lead to, or what is the purpose of the action. So I think this is, if you think of a new unexplored area you want to jump on, so this may be one of the areas which people looked at least. So here are some ideology. So what I think is for future challenges. So vision is person-centric. So why do we do computer vision? Because we want computers to learn something about the world, but about our world from what we know about the world. So vision is by itself, it's person-centric, and so actions of people, we can see it as a mechanism to reveal the function of objects. So we can maybe describe, write lots of programs to explain computer, what is important for us people, what is not, but actually by just making computer in a clever way to watch lots of videos and reason about this may give opportunity to computer to automatically learn what is important for people if you look at human actions. Okay, and future challenges, so function, function, this is, so what can we do with the objects? Prediction, this is if I run over through this taxi, so I can get killed if there are other cars driving in this direction, and recognizing goals. So all these are very, not directly maybe related to applications, but these are areas of computer vision which are interesting and open until now. Okay, so now so you can believe in all this, or it doesn't matter, but even if you don't, so still I would argue that people are very important, especially in video. People are very special objects, and one way to argue this is to answer a simple question. So the question is, how many pixels do you think if you watch TV or movies or YouTube? So how many person pixels do you think you see there on average? How much? Well, average, say TV. You have the. Okay, so that's pretty good. 35 is pretty good. So, well, I was surprised. I thought it's much less, but it's yeah. So it's lots of pixels belonging to people. Now, okay. So what? So this again relates to applications. So what kind of data do you want to analyze? So we have the professional archives, so BBC, all the TV archives, YouTube surveillance, and in all this data, so there is lots of person pixels. So if you want to understand this data, so it's important that we do something about person pixels. Okay, so this is the motivating. All this is motivating. Why do we care about humans and human actions? Okay, so what is this course about? So. So I will go through more formally, so maybe, okay, a little bit not very formal, but still, so try to say what is our goal of action recognition, what does it mean to recognize an action. So, and I will talk about, during today and tomorrow, I will talk about quite recent and a bit less recent methods, which are good to know. Current benchmarks, so how people test. Currently, what is good performance, what is bad performance, and promising future directions. And tomorrow, as I said, there will be a practical exercise on human actions. Right. So, what is action recognition? So, what is an action? So this question, so it's the terminology. Unfortunately, it's quite ambiguous at the moment. So it's. So there are many papers, of course, but some people, the terminology is not unified. So something, what people connect action in one paper is not the same in another paper. And so there are action recognition, activity recognition, event recognition, and so basically I want to say that there is no clear definition what it is. So one maybe a more stable terminology is that action is something momentary, so what happens maybe over a few seconds. Activity is higher level, so cooking or getting money from ATM. Event is more, even longer, so a football game or this type of event. Right. So, and what do we want for the computer to output? So they could be, as Andrew was showing today. So they can be different levels. So you want maybe attach a label. You want to say where it is, and in video, of course, you maybe want to say also when in time does something happen. Okay. So classification, say that this person is walking. Detection could be maybe putting a bounding box around the person. And maybe temporal detection could be, so if you okay, so the group activity, of course, is interesting too. So saying that people are interacting between each other, so saying that segmenting video temporally into saying that here is the one action, here now starts another action. This is, of course, another interesting output. Okay, so how people evaluate results. So I will come back to this at the very end, but maybe just for you to have an idea of what kind of data people are looking at. So there are several data sets. So this is a simple data set developed maybe 7-8 years ago with a simple background. So people worked on this, and the performance is quite saturated. So it's not considered interesting anymore. So there are more interesting data sets, for example, collected from so I think this is YouTube, so some sports videos from YouTube. This is also YouTube. So this is animated, well, not animated, but staged surveillance events because of, everybody seems to have problems with surveillance, so it's hard to get the real data, so people have to imitate some strange actions. Okay, and this is from movie data set, which I will talk more about later on. So this is a real data set from TrackVid. So this is from I think Gatwick Airport in London, where they filmed about 100 hours of videos of real stuff. So and annotated it. So there is. So this is the task here is to detect, to classify and detect actions in time. So to segment the parts of the video which contain, for example, running or answering phone actions. Okay, so what is the difference between this data set? So of course it relates to the difficulty of action recognition, and this can be because of the clutter. If the background is homogeneous or not, of scale, priority of actions, how frequent, like if running maybe happens more frequent than answering phone, and also important, so clear definition of training and test set. So if you do experiments, so it's very important to compare results in the paper. It's very important to have a very clear definition. What is a training set? What is validation? What is test set? Okay, so this is for reference. Maybe it's on the slide, so you can, if you are interested in action recognition, you can come back and look at this. Okay, so that was about the motivation. So I will talk next about a quite big area, which is human pose estimation. And so this is actually not my work. So much of this work was done by Andrew Zimmerman. I will show some of his slides, but also the slides of other people. So what is pose estimation? And so pose estimation is basically saying where is the arms, where legs, where all the parts of the body. And here are some results. Here are real images and real results from a few recent methods. This is kind of good output, which we would like. So here the result is in 2D. So basically we have all the limbs drawn in 2D, but you can, other methods also try to, from single or stereo images, to get also 3D people. Okay, so why, so okay, we have obviously lots of different poses. So why poses is, why is it related to actions? Obviously because actions are often characterized by different poses. So here is again, so this is a slide from Andrew. So this is a very nice picture. So you can, by looking at poses, so it tells very much what's going on here. So here are some examples from a Pascal challenge. So Andrew talked to you about Pascal challenge for image classification and object detection. So here is another part of the Pascal challenge which cares about action classification. So here it was started last year, and I think this year they have the second version of it. So what's the goal? The goal is to, given the person image, so we want to classify whether the person is talking to the phone or motorcycling, or if it's riding horse. And okay, so this is a well-defined problem. So, and it's static images, so it's quite hard to do because in video you have motion cues. I will talk about this. So here is a task which is recognizing actions in static images. Okay, what are the challenges? So challenges, okay, all the challenges which we have for object recognition, which could be the background clutter, the different view poses, clothing, so all the problems in object recognition, they're of course present for action recognition as well. And right, so there is, it's hard, yeah. So the clothing make it, especially the clothing makes it usually very hard to do it. So here, I don't know, maybe you've seen, I'm sure. So how many of you have seen this image before? Good, okay. So I think yeah, everybody knows this image. And how many of you know what it means? Okay, I thought I will not have to explain it at all, but okay. So what it represents? This is a now canonic image to when you talk about parts and relations between parts. So you think of many of the current methods for object recognition are thought of in terms of parts and relations between parts, because we want to model non-rigid objects and maybe different 3D views. Okay, so the parts are obviously eyes, hair, and so on, and the relation between them somehow represents usually geometric relations. So what is below what, maybe something cannot be stretched apart. So, and this is very, especially for human understanding of parsing the body pose, this was quite successful. So I would say probably most of the method by large, they are in this paradigm. So what is this, how does this paradigm translate? Basically, you can imagine, so you construct your model of a person by saying that all my limbs, and depends on how your granularity of your model, but you say all limbs which you are interested in, they are nodes in the graph, and then there are some links between the nodes which say, for example, that the leg should be attached to the body and that the arm cannot be like twisted backwards. So you can impose then, by specifying the relation between parts, you can encode some physical properties of the human body. And then you want to enforce these properties as constraints when you try to solve the pose estimation. So there is a line of work of trying to explore these type of models and to analyze person images. So we see some early example, 99. It's not the first one. And so this is just example of performance which this method could achieve. So about 10 years ago. So we see that well, it's quite good. Actually, on such poses, so it seems that it's a hard pose because it's unusual. But actually, these poses are easy for method because when you stretch your arms and legs, these poses are easy. Well, it's easy to localize the body parts. And so most of them, so they were relying on background subtraction. So background is otherwise is a complicated problem. So examples, so if you see the background is static, so 10 years ago, so it was possible to, sorry, not static, well, rather homogeneous background, so it would be fine to solve such examples 10 years ago. So, okay, so let's look a bit more into the methods. So, because lots of methods use this framework, graph framework, And so it's worth looking a bit into it, not too much, but I still spend some slides. So as I said, so it's represented in terms of a graph, so where you have the nodes belonging to body parts and the links, the relations between them. And in a sense, so if you remember the talk of Karsten Rother, or generally if you're familiar with CRF models, so this is quite similar. So there, for example, what Karsten told you about segmentation, you would define each pixel maybe of an image as a node, and then you would have links between them to model the relation between pixels. So here it's in principle the same, whereas the nodes are body parts and the links between them, they are relations. So, and then once you have a graph, so you typically write the energy of the graph. And the energy of the graph, it depends on usually two terms. One is a so-called unary term, and another is binary term. So what is unary term? It's up to you. So you can define it as you want. For example, if you look for hands and faces, maybe you put function f. Here is, for example, skin color. Okay, so it's quite simple, but it will work to some degree. And pairwise terms, you can either, okay, so you can do many things. So skin color, maybe it would be, you can train a hop descriptor for face or for other things. And the pairwise term, so you can either, well, the simplest maybe is to just create it by hand, saying that, okay, so the connected body parts, you draw a link, and then you say that connected body parts should not be far away from each other. Construct some function. Okay, of course, it's now when the goal is now to minimize or maximize whatever, depends how you define the potentials. This energy, and hope if the energy is well defined, if you did good engineering job to define these potentials, then it hopefully should give you a good result. So, okay, so if you try to solve this function, so what are the good and bad things? So good, of course, okay, if your function is good and if you are able to solve it, it should give you a good result. What are the problems? Problems that the state space here is very large. So if you compare it, for example, to image segmentation, so you have lots of pixels there, okay, and maybe each of them maybe have 256 gray values, or maybe if it's a binary segmentation, so it's just two values. So the state space for each node of the graph is not very large, while you have lots of nodes for the image segmentation case. So here is a problem different. So here actually the number of nodes is not a bottleneck. So the number of nodes is just a few, because this is the number of body parts. But this number of states for body part is huge, because what is the state for body part is a position in the image. It's maybe the angle and the scale, okay? And if you discretize all these, so if you take all possible positions, angles and scales in the image, this is going to be a huge. So very easily you come to these numbers of all possible body configurations. Of course, none of them are valid, but before you impose constraints, so you arrive very easily to this type of numbers. And so if you want to investigate all of them, so then so this becomes intractable. So what are typical solutions? So one approach is to look. So why is this complexity? So this complexity happens if we connect all the nodes by links and try to solve the general graph problem. However, if we reduce the full graph to a tree, then, as you may know, so the solution suddenly becomes not exponentially expensive, but becomes polynomial, because so we know there are dynamic programming methods, right? So which can solve the which can solve the tree in a polynomial time. So how many of you know about this? See. So dynamic program. How many of you know dynamic programming? Okay. So if you know dynamic programming, so you know that you can solve it in a sequence, And trees are is just a special, it's a more general case of a sequence. So you can, it can be solved in a polynomial time. So this is good. So that's what lots of methods do for pose estimation. Of course, it's not optimal because this tree structure is can have faults. So here is one example of a failure of due to tree structure. So here are two arms which are locked on the same, two hands locked on the same hand, and so this is plausible configuration, but maybe it's less likely than basically what is missing here is that that the two hands of the model, they know nothing about each other. Okay, they're conditionally independent. So what would be interesting to introduce is to have a link between two hands and model, for example, that two hands don't often appear at the same place. Of course, not sometimes it happens, but maybe not very frequent. So with a tree structure, this is not possible to do. With such a structure, this is possible to do. Just put some penalty for one hand being over another. But the problem is now that this is not a tree anymore. And in principle, so solving this is again NP-hard problem. Okay, so these are issues with the current pose estimation methods. So pose estimation is a very hard problem, and it's a very active problem also. So here are a few methods from the past, and here are four papers just from the CVPR conference this year. So as you see, this is very active field of research. So maybe I can just leave the references here, and if you are interested in pose estimation, so you can look more into them. Basically, so they are all these three methods, they are developing better unary terms. So if you remember, the energy function has a unary and binary term, so they are developing better models for recognizing the limbs of the body by training, for example, Hawk descriptors from lots of training data. So, so if you want, so the keywords here is a poselet. I don't know if it's yes here. So poselets are just the idea of that you use lots of human annotations to train part detectors for not just for the face but for many different body parts. Then you put into the model and usually it performs better. Okay, and this paper, so you've heard from this a lot, I suppose, from Andrew Fitzgibbon and Andrew Blake from Microsoft. So this is the prize-winning CVPR paper, and I guess the Microsoft advertised enough. This is the fastest-selling electronic device, whatever. So the Kinect. So Kinect, of course, is a great thing. So it's you can think that it does. So it does exactly solve the problem of pose estimation. It does it very good. So if you played Kinect, so it's quite amazing what it does. So however, so there are of course limitations. So do you know what are the limitations of Kinect pose estimation? Distance is one, yes. Yes, yeah, that's good. Yeah. Yes, no, that's true. Yes. Right. So if you turn, of course, if it doesn't see arms, yeah, it doesn't see arms. Sorry. Okay. Is it? Okay. Because you mean shiny. So okay. Maybe. So one major, yes, more. Exactly. So this is one of the big things. So I think the distance and, I mean, of course, if you turn off the light, then nothing. Okay. Actually, if Kinect works, if you turn off the lights, this is good. Yeah. But of course, you can corrupt things by many things. But I think the principle currently, maybe it will be solved in some future, but so the distance and the indoor requirements. So it basically it provides a very good tool for close range indoor environments, and for gaming this is perfect. But if you want go outdoor, or if you want to analyze lots of movie archives which are already recorded a long time ago, so you are still with RGB pixels. So the problem people trying to address here from RGB pixel is still a valid problem. Also, of course, we should think of not overdoing. So if there are applications where we can use this technology, of course, we should not. Why not use it? Okay, so here are just a few demonstrations. So here's the work also from Andrew a few years back. So this is a demonstration how we could use the pose, how we can demonstrate that the pose actually works in such very complicated scenes like this, for example. So what they did, so they have a pose estimator which they will run on all the frames of several movies, and now given just one guy in a specific pose, they want to retrieve all the other people with the same pose. And so here we see a few examples, and we can appreciate also the difficulty of the images, because there are lots of clutter and lots of different clothing and so on. So here's another one, query, so standing pose. Okay, so here are just a few slides. So this is another interesting application of pose estimation for recognizing the sign language, also done by Andrew and Mark Everingham and Patrick Buller. So what's the goal here? So the goal is to make computer learn lots of sign language, or to understand the sign language, for example, shown on TV. So what applications, I don't know, by imaging, so if you want to interpret automatically, so it can be quite nice. So now the goal of this paper is quite interesting in itself. So what they try to do, they try to throw into computer lots of videos with the sign language and also with text. Okay, so the sentences. Okay, so the input data basically looks like this. So they have many sequences of sign language and the corresponding sentences in English. And now what they want to do, they want the computer automatically trains learns the different signs for the words. Okay, so basically do this sign word mapping, the visual sign language and the words in the text. And they want to do it completely automatically. So basically the input is text and videos, and the output is a classifier which can watch the sign language and output the text. Okay, so the interesting part is that there is no manual supervision here. And so this seems like a very hard problem, but actually this is interesting problem, and it's possible to solve it, because now, of course, if we are given just one sequence and one sentence, okay, so the problem is almost intractable, because if you don't know sign language, so you don't know what is what. However, so if you have, you can exploit the redundancy of data, because we have lots of hours of video, so we can fit in, for example, lots of video clips and the sentences, and then exploiting redundancy and trying to cluster together the words, and also finding out what is common basically between all these sequences. So hopefully things which are common, they should correspond to the tree. Okay, of course it will be noisy, but the more you should hope that the more examples you have, the less problems you should have. And actually, this is known. Okay, so this is known as multiple instance learning. So in machine learning, people address this problem quite well abstractly. So the abstract formulations that you have, you consider not just one example. So you consider the bags of examples, and so you differentiate between positive and negative bags. So the positive bag is something which has positive instances inside, and the negative bag is where you know there is. So this would be the 3 words, and this will be nothing. So this will be no 3 words. And so there are formal methods. I'm not going to do it, but there are formal methods how to deal with this problem and how to separate them. So here you pretend you are a computer and you are given this, and you try to now to learn what is the golf sign. Okay, so you guess it probably from the first one, but computer doesn't know anything about the golf. But when it watches many videos, so eventually it will pick up the sentences, all the words. Okay, and so here are some signs. So the power of the approach is also that it's not just for one word, basically. You can learn the huge vocabulary for lots of different words without any manual supervision. So you just throw in the videos and the text, and hopefully if the algorithm is good, so it will produce classifiers for lots of different words, and then you can use them. Okay, so what are the problems? So one problem is truncations and occlusion. So here are 2 examples. So here's a truncation by the image boundary. Here's a truncation by occluded persons, by other objects, and so this is quite a big problem because so the method, whatever we train, so it doesn't know anything about the rest of the scene. So it just looks at the person and try as hard as it can to interpret the pixels being human. But if there are other objects which are occluding, so it knows nothing about them. And of course, the obvious direction, okay, so why don't we try to think that this is a cornflakes box and so on, but this becomes very hard because suddenly you have to interpret not just the person, which is already very hard, but you have to interpret the whole scene. And we are not there yet. Okay, so okay, I've been talking about the human pose, and initially, so actually the topic of the lecture is about human action, so a reasonable question to ask, is it always necessary to recognize the pose? So I hope, so in the beginning, so I provided a few examples showing that the pose should help action recognition because they're related. But now the question, okay, if the pose is really so hard, do we have to try harder and harder to get perfect pose estimation and then switch to action? So maybe not. So here's a very nice work. And also Andrew mentioned today something about latent variables. So they try to use pose estimation as a latent variable for action recognition. So what is a latent variable? Basically, latent means that the output is not visible in the output. So it's something hidden inside the algorithm which should help it to do a better job, but it's not the part of the output. And this is when, if you're interested in action recognition, if you're, for example, interested in people saying that these 3 guys there are sitting, so this is the output you want. So you don't necessarily need to say exactly where the limbs are because it's actually a harder problem. So just putting a label on it is a simpler problem than exactly specifying where the limbs are. Okay, so this is a nice work because it treats the pose estimation as a latent process, or the pose of a person is a latent variable. And so what we see here is that okay, so basically during training, so it tries to learn parts of the pose which are helpful for particular action class. So what we see here that it does correctly recognize people sitting, and all probably the parts of the pose which are important for this action, these are legs. Okay, and it does correctly recognize the leg position. Then it doesn't, so the rest of the body is not correctly, the rest of the pose is not correctly estimated, but this doesn't matter, right? So it's not critical So basically it tries to pick up the best things, the important things from pose estimation and use it for action classification. So here's another example. So this is not about poses. This is about objects and it's about poses. It's about objects and poses. So what they try to do, they try to estimate pose and detect objects like rackets, for example, or the ball simultaneously. So separately, this is a hard task. But because of the constraints, for example, the racket is always usually in the hand and the ball is somewhere close to the racket, so they can explore these constraints and do both tasks of racket detection and the pose estimation better. So if you do the same algorithm done separately, so these are the output of racket detection, this is pose estimation, but if you do them jointly, so this helps. Okay, and now so I talked a bit in the beginning about function, and so it would be interesting if our computers would start interpreting, not just putting labels onto things, but also saying what is the function of objects. And so here are examples also from CVPR this year of two nice works, which actually none of them knows anything about, so the programs don't know anything about the type of object, if it's a chair or if it's a bed. However, so they tried to, from geometric cues, you can from single image or multiple images, you can extract simple geometric cues. So, for example, the surfaces, rough surfaces. So it doesn't. So you see here the estimates of the 3D is very rough, but still, so with these estimates, so they can arrive to interpret the image. For example, saying that these are the surfaces where the person can lay down, or these are the different surfaces where the person can reach. And this is not pose estimation, it's not object recognition, it tells us something functional, what can we do with the scene. And for some application, this is the output, which might be most interesting. Okay, so I'm going to have a short break. So maybe in terms of conclusion, so this is one important thing to remember. So human poses is an interesting topic, but it doesn't mean that human actions, and human action doesn't mean poses. Okay, so let's resume. So last half an hour for this evening. So I was talking about the pose now, so I'm going to switch to action recognition and also in video. So most of the rest of today and tomorrow it will be about video. So here is a schematic slide showing how you can think of doing action recognition. Actually, this can be thought of for other computer vision methods. So usually you have some measurements, you have some models where you encode your knowledge. Maybe it's some constraints about your limbs, or if it's you eat in the kitchen and so on. Okay, and then you want to, given the data, so you want to do the association between the model and your measurements. And during training, so you learn this association, and during testing, so you try to infer it. Okay, and okay. So we are going to look at a few different types of measurements. What can we do? What kind of measurements can we get from mostly videos? And also, so what kind of models can be trained for actions? So if you think of video and action recognition, so this is maybe the most straightforward thing, which probably half of the people would try because it's very easy. But then it doesn't work, so people go somewhere else. But so this may be the simplest way how to try to interpret the video. So you have a human figure. So if you have access to background image, or if you can do some segmentation, and segmentation in video is sometimes easy because what is called motion-based segmentation. So if you observe the difference in the pixels, so this is likely to be due to motion, so you can just say that these are moving pixels. And once you have these, so for example, so here is an example of early method, so-called temporal templates. You can do it, of course, for many different frames. So if you're interested in temporal evolution of these silhouettes, you can summarize it, for example, in something here called temporal templates, where the value of the pixels encode the time. So how long time ago this pixel was observed. Okay, so this is a very straightforward implementation, and now we can we summarize the whole video into just one image, and now we can apply whatever. So here they applied some moment invariants to describe this type of image, and so this is the data set. So this is early work, so maybe 10, 15 years ago, where they had a data set, simple data set with a very simple background, very distinct actions. So simple nearest neighbor classifier gives something around 66%. Nevertheless, there are many classes. There are 18 different classes. So 66 is maybe reasonably good. Okay, so what are the problems with this? So here are some, okay, so why is it good? Because it's simple, fast, and works in some very simple conditions. So they were 10 years ago, actually, this is work from MIT Media Lab. So they were able to construct some simple interfaces, so gaming interfaces for kids and so on. So it was when the background is controlled, when all the settings are controlled, this is a simple way how to recognize actions or interpret videos. So now where does it break? So here is an obvious problem. So we see some pixels missing, some pixels are there because of the shadow. So segmentation is hard. You can try to improve it, but in general it's hard. Okay, and sometimes it's even not clear, because if you want to, okay, here maybe you can come up with some good segmentation. Here it's very difficult because everything is moving, so motion-based segmentation will not help you. And even worse, so if you're relying just on the silhouette of the person, it's sometimes it tells what's going on, but not always. For example, here, so you see the drinking action actually doesn't appear in a silhouette. So if you just have access to the silhouette, it's hard to interpret what's going on. Okay, so nevertheless, I'm going through very briefly about some work which was building on the silhouettes. So how to improve? So say if we want to improve this method, so how to do this? So one straightforward way is to say that, okay, so this is a silhouette, but it's not really valid silhouette. We know what's the space of, we approximately know how should the human silhouette look like. So we should not just do the dumb segmentation, we should impose some constraints, some prior knowledge, okay? Restrict the space of admissible silhouettes. And so how to do it? So there was a quite nice also work about 10, 15 years ago. So, and it's actually quite useful for applications in medical imaging and also for face tracking. So basically what is this about? This is about restricting the shapes. So you are not considering all possible shapes, just a subset of shapes. So you represent the shape by points, okay? And then you collect many examples of this silhouette, or the shape doesn't have to be silhouette, it can be any shape. So they also called point distribution models. So the important point is that these points, they should have correspondence, okay? Then you, for each silhouette or each contour here, you stack the points, the coordinates of every sample into big vector, and you have lots of these vectors. And now because you are looking at a particular shape, for example, human body or face, so they're going to be very dependent. So there will be lots of points, maybe say 100, 200 points here. So you'll have a vector of size 400, but actually the dimensionality of the data will be much smaller because the samples will be very similar. So to capture the variability in the data, so what you usually do, you apply linear methods, and this is PCA. So how many of you know PCA? good, fine. So then, so this is a, so if you do PCA on all these vectors of shape, so you will get something like a shape space, and then if you, so with very few coefficients, you can produce all possible shapes of your data. So this is quite neat, and for example, what it can do for you, even if you estimate some point wrong, you project it to PCA space, you project it back to the silhouette space, you can even correct some mistakes, so this is all nice. And okay, so this, for example, for faces, you can use it to align faces, and there is actually still quite lots of work using this or developing further these methods. Maybe not just based on contours, more sophisticated methods, but people work on this still. And okay, so for actions, so you can now, if you restrict all possible shapes, so you can now apply it to, you can search it over the image and do much better than just doing thresholded segmentation. Okay, so this is nice. So what else can we do? So there are, of course, failures, and so it's all about. So what I'm talking now is about imposing more prior knowledge. Okay, so if starting from raw segmentation is not good, so we can impose prior knowledge on how the shape looks like. We can also impose prior knowledge of how things move, because if a person is for example, walking, so observing one frame, if it's you correctly estimate the shape of the body, it's this prior is very strong what is going to happen in the next frame. So there are very few possibilities what can happen in the next frame. So it's also reasonable to talk about the not just shape prior, but also the prior knowledge for motion, okay, or for the temporal evolution. So okay, so if k is a frame number, so the goal is now to infer the shape in frame k from k minus 1. Okay, and one can learn, so again, so linear models for this. So here is one type of linear model called autoregressive model. So so basically it's a linear model, so x is a shape in 2 frames, and then you can learn this model from training data. So if you have a very simple sequences where people walk, for example, you can learn these matrices from neighboring frames. So learn the prediction what can happen from one frame to another depending on the state. Okay, so here is a demonstration of visual demonstration what it means to learn the dynamics. So now it's so this is, by the way, work from Cambridge, from Andrew Blake, at the time he was still in Oxford. Sorry, from Oxford, yeah, from Oxford University. Okay, so what happens here? So the measurements now, they are just points on the 2D surface. Okay, so there's somebody who is drawing a name here, Andrew, and so the observation vectors, these x vectors, they are just xy coordinates of the drawing here. Okay, and what is learned? Is this then 4x4 matrix A, which basically captures the transitions, linear model to capture transition from one point to another depending on the previous position. Okay, and so here is the realization of this model without any data, so just driven by noise, by the way. So here is a noise factor. So if we just put noise into system and try to predict and predict and predict and iterate, so we will get something like this, and we see that it's not, linear model is not, of course, enough sufficient to exactly reproduce this type of this word, but the behavior is somewhere close to what we see here. Okay, so this is just visualization, and for now, if you have more complex model of a silhouette, for example, so you can also just predict what's going to happen without even looking into data. You can also do this for, so this is a linear prediction model. So this is, you learn just one model for particular type of motion. But now, for example, if you have running, jumping, say, and walking, you can learn 3 different models. And also you can try during tracking, so you can try to estimate which of these 3 models is currently valid. So this is exactly what happens here. So this is an example with a line drawing, and there are 3 classes of motion learned here. So one is a line drawing, basically the lines, and scribbling and doing nothing. And okay, so the point here is that it actually switching between these models, it helps tracking. But at the same time, so it is a kind of action recognition. So when you have the switch of the model, you can, it's a discrete set of actions. So you can say if it's a line drawing or scribbling, for example. Okay, so I talked a bit about shape models, appearance models. So now I'm going to talk about motion. So maybe I've shown already this. So do you know what this is? It is a football. Sorry? Yes. You're too clever, you know everything. So it's, yes, so basically this is a, but if you didn't see this image before, so it's very hard from a single image to say what it is. And obviously when you see the motion, it becomes much easier. Okay, so I'm trying to convince a motion is an interesting cue. For example, so if you would have perfect motion estimation, it would be invariant maybe for different trousers of this guy. So if you have a good motion estimator, maybe it will just produce the vector field, which is invariant to many different things. And again, so I'm going to, okay, so here, this one you've seen already. And so I'm going to show the original video from this Swedish psychologist. It's very old. So it's from about 71. And so these are the guys making experiments. And so what they're looking at single dots and then pairs of dots. And this is still quite ambiguous, but when you start getting a few more dots, like 3 dots, so then it clicks, you know what it is. And this is quite striking, yeah. So this was both from, I guess, from people who study human perception, but also for computer scientists, especially at the 30 years back, when the computers were very, very slow, so compared to nowadays. So it was an evidence that with just very few measurements, humans can do a lot, can interpret lots of things. And of course, so by the time there was lots of efforts dedicated in building the models which could interpret such dot patterns. And it's probably still used, so people use, when you do motion capture data, this is the type of pattern you get, maybe with 3D. So yes, it's quite funny. Okay, basically motion is a very good cue. So the problem with this method is that they are, so if you have these dots, if you are sure you detect all the dots you need, so the problem becomes very easy. The real problem is how to detect the limbs. And if you want to do this, we are back to the pose estimation problem, basically. Pose estimation in every frame in a realistic condition is a very hard problem. So it's, if we solve it, so it will be great, but we cannot solve it yet very reliably. So even if we cannot solve pose estimation, so still believe that motion might be a very good cue. And probably, so if you look back at this guy who is a 30 pixel man here running, so run. So you probably, well, we don't know what happens in our heads, but probably it's unlikely that we are doing exact pose estimation for this guy. So it's maybe something much more simple should give us cues. So I'll spend maybe 2-3 slides on motion estimation. And so in generic sense, so this is optic flow, so-called optic flow estimation problem. How many of you know about how to estimate optical flow, what this is? Okay, so not that many. Okay, so what is optical flow? Optical flow is so we have a 3D world, we have fourth dimensional time, so we have 3D vectors, basically, so the one time frame to another in 3D, so we have a vector in 3D, so this is the motion in 3D. Okay, and if we project these vectors into image plane, this is optical flow. So it would be great to estimate this, and it's possible to do sometimes. However, it's not always possible. So the problem is is ill-defined. So when is it not possible? For example, here are 2 examples where we have one sphere. It is rotating, but it has no texture on it. So it's and we have a light source, and it appears that there is no motion there. And here the opposite example. So if the light source rotates, but the object is static, no texture. So these are examples where it's just not possible to recover physical motion from the images, no matter how you try it. Yeah, so these are quite specific examples. So in many cases, it's possible to estimate motion, and there are lots of algorithms. And the topic is really old, but it's because the problem is ill-posed, so there will be never perfect solution. However, people try to improve. So there are many methods. Okay, so what maybe the main story of all these methods? So most of them, they impose constraints. And the most common constraint is a brightness change, so-called brightness change constraint. It says that all the differences, if we look at different frames, and we look at the differences, what happens with the pixels, it says that all the differences due to motion and not anything else. So what would be the violations if you switch on, switch off the light? Then the gray value changes would not be because of the motion, it could be because of different factors. Okay, so this is quite important constraint, and under this constraint, it's actually possible to solve the problem in many cases quite accurately. So in terms of formally, in terms of equations, this brightness change constraint. So again, what is brightness change? So the gray value only changes due to motion, nothing else. So it transforms to this equation, so-called brightness change constraint equation. So what this is image gradient. So this is Ex, Ey. V is a velocity which we try to estimate, and this is a temporal derivative of the image sequence. You take the difference of pixels over the over time. Okay, so fine. So this is this is good. The problem is that we have just one equation and 2 unknowns, because V is a velocity in Vx and Vy. So if we have one equation, 2 unknowns, typically what you do, you take, if you want to stay linear, so you may solve it in a least square sense. Right, so least square sense means you collect lots of measurements, maybe so if you want to estimate motion in 1 pixel, maybe you will collect a few measurements. So what is the measurement? I guess this is the gradient. You collect the measurements around this pixel, and then you have the least square solution for it. Okay, so you estimate V now from this matrix, so it's all fine. And actually, so this, if you Andrew probably told you something about the Harris point detection. So this is a second moment matrix, which is used in many different cases in computer vision. Fine. So okay. So actually, there are still some problems with it, and that's why the optical flow won't be ever solved, because it just not always works. So when is the problem? If this matrix has rank 1, so we hope. Okay, so we hope to add more measurements and to add information. But actually, if this matrix has rank 1, then or 0, then by adding more points in the neighborhood, it doesn't help us. And this is a typical case. So, for example, if you want to estimate something here, the motion here, and we collect all the points from the neighborhood here, all the gradients, they will be pointing in the same direction. So if we try to solve this least square equation system, it actually it's still under constraint. So it's a different, so if we have a corner, then the situation is different. Because we have gradients pointing in different directions, and the matrix is rank 2, so it's fine. Okay, it makes sense, because if you imagine if you just look at this circle and you see something moving here, so we don't know if it actually moves there, there, or there. But if we see the corner, so it's clear where it moves. Okay, so this is very, very brief introduction to optical flows. Again, so there are lots and lots of methods. Actually, so if you're interested in optical flow, here are 2 recent papers, so 1 paper and 1 master thesis from MIT, and the code is online. And the code is, so I'm not really expert in optical flow, but this is probably the most recent and state-of-the-art code for optical flow estimation, if you are interested in. Fine. So okay. So this is generic optical flow. Now, so again, so for pose estimation, maybe we don't actually. If our goal is to recognize actions, maybe we don't need to solve the optical flow estimation first and then move to actions. So maybe we can do something smarter. And so one thing we could try is to use instead of trying to solve generic problem, maybe we can solve more specific problem of optical flow estimation, which is related to action recognition. So here is one way to do it. So instead of trying to solve this vector v in every pixel, you can try to solve. You can try to make your model more complex, more sophisticated, and related to your actual problem. So here is you can see this method as extension of standard optical flow. So what happens here? So instead of v is just a direction, motion direction at one point. So you extend it to something bigger vector, and what this bigger vector, this encodes the motion in a patch. Okay, and so what are these motion in the patch? So you can now, so for example, say you are interested in lip motion analysis, okay, or maybe you want to do lip reading from video. So what you can try to do, you can apply whatever optical flow estimation method you have. You collect lots of patches with the optical flow, and then similar as for the shape models which we've talked before. So you can now do a PCA. You do PCA on this data. So you take all the flow vector, you stack them into a big vector. You do the PCA, and then you get the basis, which is describes the motion for this particular problem. And the interesting thing is that once you train the basis, the interesting thing that you never need. Okay, so if you want to say reconstruct the motion, you never need to estimate the optical flow again, because all you need is to estimate the this vector directly, and this can be done in the least square sense, in the sort of similar way. So basically, it will be a bigger matrix here, and you will have a W vector here, and so you'll be able to get these motion patches directly without optic flow estimation. So why is it good? For example, here are some examples of speech, and so here are different people pronouncing the same letter, and what is plotted here is the value of a coefficient for particular basis function. So what we see is that different people, when speaking the same letter, so they produce quite similar coefficients in terms of the basis function, and this can be used directly to recognition. So what it says that you don't really need to capture. You can use motion cues without really computing explicitly optical flow. And so this is good. So you can use lots of training data to constrain your problem. Okay. So here is another example of. So this is the work of EFROS, and so here they say, okay, so we just take whatever optical flow can deliver us. So here are noisy optical flow vectors on this image. So just to remove noise, we can smooth it. So they separate motion into different directions, and they apply just Gaussian smoothing. And actually, so this corresponds, although it's not said in the paper, this corresponds to kind of sift, optical flow sift. So they compute, in a sense, the histogram of optical flow directions here. Okay, and this can be useful, for example, just to do nearest neighbors matching. So if you have two sequences, many frames, you can match frame to frame. So here is frames of sequence A matched to all frames in sequence B. Okay, so this is time and this is time. Now, so this is you see this matrix has diagonal structure. Any idea why it has a diagonal structure here? What can be the reason for this matrix being diagonal? So if it would be the same sequence, so the diagonal should be strong, right? Because then the frame should match to itself. So okay, actually here we see several diagonals. So why? I don't know why. Right? Yes. So if you have, for example, walking pattern, so after say this is the period, say this is the say 10 frames, and it would be the period of the walking action. So you can they repeat. Okay, so of course they don't repeat exactly, so we don't have the very clean matrix here. So if we know it's a repeat, we can impose some smoothing prior by just maybe filtering this matrix a bit, and then we can do nice motion or sequence matching, frame to frame sequence matching. And what is it good for? So this is an example from their nice work, and also an example which you've seen at the beginning of the slides today. So what they're able to do, they have this guy running, and they have big data set with the small patches of people doing different things. And now by matching the optical flow on this guy to optical flow on all these other guys, so that they're able to retrieve nearest neighbor similar examples from the data set. Okay, now imagine if this is you, so you can pretend to be the real football player. And you can, if you are good in graphics, you can copy paste yourself into some other video sequence. So that's how the video with this red guy, which I've shown in the beginning, that's how it was done. Okay, but okay, not just for graphics. So if you are able to match, so of course you can also do recognition. So how if all these your data set videos, and they also have labels, then you get your input, you match to, for example, these, and then you can attach the label and do recognition. And it works quite reasonably, so they tried it on different data sets. For example, this aerobics data set, so it works much better than the other methods which I was showing before. So here are some tennis sequences. So this is all simple nearest neighbor classifier based on optical flow. So this is all quite simple, and in this, so we see it does a quite good job. So just one last thing for today. This is another system which also does matching based on the motion. So it has two patches. So here would be the right. So this would be the template patch, and this is the patch from space-time patch from the test sequence. And the goal here is to, okay, let's say optical flow estimation is no easy process. Maybe we don't want to rely on this too much. So what they try to do is to match patch from the test sequence to the training sequences without computing any optical flow, but also without computing any specific basis, because they want to match any motion, not just lips or legs. They want to match any types of motion to each other. And so what they do, they separate these patches into even smaller patches, and then check that they assume that these smaller patches, say cells, that they have constant motion, and they constrain the corresponding, so basically the middle of this bigger patch and the corresponding middle of this bigger patch. If these bigger patches should be the same, then the smaller cell patches should also have the same motion. And this constraint could be imposed easily by going back to optical flow equation, where, okay, maybe just scrolling back where here we were trying to solve for V using this equation from a single patch. What they do now is they put two these matrices, one coming from the training video and one coming from the test video, and they require this equation to hold still. Okay. So basically, okay, so you can if you're interested, you can look in the paper, but the main idea is to avoid, again, explicit optical flow estimation, and but still be able to compare motion without optical flow estimation, which is complicated. Okay, so here are a few results. Again, so this is very, so this is a template video, and now they have a ballet video, and they do the scanning window in space-time, and they try to match this template to all the temporal sub-windows of the test video. And good, so here's another one. Okay, so here, the point here, there is no training, so it's nearest neighbor retrieval. And it's generic, so it doesn't have any particular model of an action, so it's able to match it. Okay, so okay, just brief overview, maybe what we have seen today. So we looked at body pose estimation, which is a huge area on itself. So you've heard about Kinect when there is no depth data, so there are lots of methods trying to solve this hard problem. And it is related to action recognition. We don't need maybe always perfect body estimation for action recognition, but it's useful. So we looked at early methods based on shape and motion priors, and we also looked at optical flow estimation methods and how they could be useful for actions. So what's coming tomorrow? So tomorrow it's more learning, so how to learn different action classes. Also, so I'll be talking about local methods, so similar to local features which you've played today in the practical and that Andrew was talking about. So we'll look at local features, seems to be very good for action recognition. And we will also look at realistic data, so all what you've seen almost now and up to now, so it was on simple, not very realistic settings. And so ultimately you want to go interpret, for example, video archives or TV programs or surveillance videos, and the data is more complex. It needs different methods, and will be the topic of tomorrow. Thank you.